Hey guys, can I get a sound check?
I can hear you.
I can hear you.
Thanks. For some reason, my camera doesn't seem to be working, but I guess that's fine. Good. Okay. Can you guys do me a favor when you when the quiz pops up and you guys are able to download it, let me know, just to make sure I don't have to go debug anything.
I see it, Professor.
Good.
Okay, great. Good luck, guys.
Professor?
Yeah,
It's supposed to be 2 questions, right?
that's correct.
Okay, just making sure because there was 4 pages and 2 of them had the name and dates, but nothing on them.
Yeah, thanks for checking that. 2 questions, and that's just extra space for you guys to, if you need extra space to work stuff out, but make sure you return like all the pages when you
Okay.
turn it in.
Thank you.
Thanks for asking that question.
Professor, I'm sorry, I couldn't remember. Since there was 5 pages in the quiz, do you want us to send back 5 pages?
Yes, please.
Okay, thank you.
Thanks. Okay, everybody, you have about 3 minutes to email your stuff to me. Just remember, yeah, you'll have to email it to me, and make sure you put your name on every page. You put your name on the file name, and you turn in 5 pages. Thanks, guys. Okay, guys, unfortunately time is up, or maybe it's a good thing. So go ahead and email it, and I'll give everybody another minute. Can you all see the prof? Sorry, guys, I have my camera's not working for some reason. I think it's upgraded my Mac operating system, and I'm just guessing I'm having problems with all sorts of permissions and stuff. So I promised I took a shower, got a haircut, everything, but you guys don't see me. Let's see. So guys, remember to email me, or don't. This is taking some time. What? What? Okay. All right, guys. So I'm gonna get started with the next chapter. So now we got through. We looked at the diodes. We saw it as a piece of semiconductor. We looked at how there was a P and an N type semiconductor, on how that kind of gave us something we call, this is in sort of semiconductor land, and this is in circuit land. So it's this exactly the same thing. Well, we call it a diode when we're using a circuit, and this is the circuit drawing of a diode. Okay, so now we're gonna, in this chapter, which is I guess it's chapter 3 of your book. We're moving on to that now. We're gonna start looking at using diodes as a circuit element. Okay, so first we'll talk about, we talked about how we had this, if you took a diode, so if we put a voltage source on a diode, Vn, let's call this Vd. And then this would be the ID. Okay, and we swept that Vd from minus infinity to plus infinity, say, Vd. What we ended up with was a characteristic that where you have very, very little current. Remember, this is I sub s, which is dependent on some diode parameters, but it's a very small quantity. It's maybe 10 to the minus 12 to 10 to the minus 15 amps. I don't think there's anything that limits, besides your manufacturing capability, et cetera, how low this number can get. That's purely a manufacturing thing, but it tends to be very, very small, very close to zero. Okay, so it's down here, it's like that. It crosses zero right at zero, and as you go sort of in forward, you end up with a, so this is, I'm sorry guys, I didn't label this axis, which is I sub d. So over here, I sub d is approximately I sub s exponential of Vd over Vt. Okay, and Vt is equal to a bunch of universal constants multiplied by the temperature T. And so if we just take a one temperature, which is, we always talk about room temperature, it ends up being 25 millivolts. Let's see, and the full equation for the diode equation is this. So what is the I sub d is equal to I sub s exponential of Vd over V sub t minus 1. So if I took this full equation, I made Vd very negative to minus infinity, this term would go to 0. Id would end up being minus I sub s, which is correct here. If Vd was 0, this term would go to 1. 1 minus 1 would give us 0. So we'd cross exactly at 0. And if Vd is very positive, this term would be much bigger than 1. So we'd end up with approximately this term, and we'd get this sort of exponential increase. Okay, so that's all the stuff we saw as a diode model from the previous chapter. And we also saw that this model, because of these exponential terms, we could have, sometimes it helps to rewrite it, just rewriting this equation. Actually, I just rewrite this one, which is easier. So I can rewrite this. Sometimes you want to get V sub d in terms of I sub d. So you could also write this. It's exactly the same thing, and just rewriting it. So what happens though is, circuits are typically many, many devices. So we might have, you'll see like pretty immediately we'll have like more than one diode in our circuits. And it turns out if we try to, plug these kind of equations with exponentials and natural log terms, et cetera, in our, circuit calculations, it ends up getting us to a pretty complex solution. In fact, a lot of times you can't get a closed solution. You can't get an exact solution. So, we have techniques to try to solve that by iteration and so on. But another thing that people have done is to create a simplified diode model. So we'll talk about the ideal diode model, which is a simplified model. Okay, and then we'll look at how you kind of analyze some, how to use that in some different circuits to get us used to analyzing it. And then we'll talk about, some like a better model called the constant voltage model. And then some of the other characteristics of a diode, like breakdown, like it's a real device. So if you put enough voltage across it, it'll break down, et cetera. So it'll have some of these weird characteristics. So we're gonna need to be aware of those. Okay. So we're gonna look at that as a diode, how to analyze this diode circuit, and when is it appropriate to use which model. And then we're going to talk about, I guess the applications really are going to be sort of coming and going through this analysis. We're going to be looking at a few different applications of diodes. So regulators, rectifiers. We're not going to look at limiting and clamps in too much detail, just a little bit to help us analyze or to sort of give us some examples to analyze diode circuits with, but so we'll be looking at some applications. So diodes are, another thing about diodes is, like it says here, you have a lot of applications, but they're also part of transistors. So you can't really understand how transistors work without understanding diodes, because it's like a transistor. I don't know how to put it, but it's kind of like, at least a bipolar transistor is pretty much like two highly linked diodes. You can't think of it as two separate diodes or highly linked. But anyway, you have to understand diodes, how to analyze diodes. Okay, so now let's talk about, this is an application that all of us can get our arms around, which is, like a cell phone charger. So this would be the little, little cube or brick that you plug into the wall outlet, and you plug the other side into your cell phone to charge the cell phone. And the problem there is that, I talked a little bit about this before, but the problem is that the power plug in the United States is 110 volt AC voltage. What does that mean? Well, it means that I'll just zoom in here. Okay, that means that it's 110 volt. When you hear 110 volt, it means 110 volt RMS. So the peak is really 110 volt. So V peak, as you go to 110 volts times square root of 2. So which is, I don't know, like 140 volts. Okay. So it means you go up to 140 volts and it's AC. So it goes to, let me make this, so it goes up to plus 140 volts and it goes to minus 140 volts. And it's doing this like a sine wave, okay, at 60 hertz. It means that this whole thing repeats itself every 16 thousandth of a second, every 16 millisecond. Okay, as it's jamming along. If you put a scope there, that's what you'll see. Okay, so that's what's coming out of the wall. And so if you look at the DC component of this, the way to look at try to find the DC component is you're going to have to take, say, an average, some period of this, right? Let's say to take one period from 0 to 0, and you integrate this thing and figure out, well, okay, how much of this is, how much of the period it's above ground and how much of it is below ground. And the difference between those two gives us the DC value. Okay. Now, because this is a pure sine wave, it spends an equal amount of time above ground as it does below ground. So it means it has this guy coming out of the wall has 0 DC component. It's completely AC. It's completely alternating current. Okay, so that's on the wall side. Now on the cell phone side, so this is the wall side. For charger. Okay, so on the cell phone side, you have a battery, which wants to get a DC voltage. You have all your circuitry that want DC voltage. So what you need, a pure DC voltage. And in this example, it's 3.5 volts. What's a DC voltage? Well, a DC voltage has no change with time. So this is like time. This is the voltage axis. And ideally, you'd like this to be a completely flat 3.5 volts or 12 volts or whatever your cell phone wants to see. But you sure as heck don't want to see this thing going up and down. That'll just fry your cell phone, and certainly won't help it charge or operate or anything. Okay, so the question is, how do we go from this input, which is the wall? Incidentally, I'm sure you guys know not most, but yeah, actually I guess it is most. A lot of the other parts of the world, stuff's running at 220 volts RMS, compared to the US is 110. But same problem in the sense that it's an AC signal coming through. That's how people transmit electricity, and how it gets to your house, to your office, etc. Okay, so the question is, if this has this wall plug has no AC component, has no DC component, is purely AC, how do we create a purely DC component out of that? Okay, so I'll tell you guys sort of the rough steps, and again, using a black box, which as a spoiler, I can tell you the primary working, the primary magic in this black box is our diodes. Okay, so we just look at a black box here, what we would need. So the first step, what you would want to do is, you have these really high voltages here. It's a kind of voltage that if you, stick your finger on, you might meet your maker, to a pretty small voltage that's not going to blow up your cell phone. So the first thing you want to do is step down this voltage. And for that, you actually can use, basically, it's essentially, I'm not going to go into it much, but essentially you have 2 coupled inductors, okay, which basically, depending on how many the ratio of the number of sort of circles you create on this side, circles you make on that one, you basically can step down the AC voltage. So it's pretty easy to get with with a couple inductors to go from 110 volt RMS to, say, a 4 volt RMS is what we did here. Okay, that one is pretty straightforward. You don't need a diode for that. But again, the problem is you still have the situation where after you've stepped it down, let's say to 4 volts RMS, or 4 volts times square root of 2 peak, you still have equal positive and equal negative side. So you still can't get a DC out of this. So what people do is they use something called a rectifier. Okay, to get rid of one of these halves. So typically you get rid of the negative side. Okay, so this was what this black box does. This black box lets you pass the positive sides, and gives you a ground when you have negative side. So this black box, basically at the output, you start looking at these two humps. Now you still need to do a bunch of processing with this, not a bunch. You need a capacitor, etc. to, Louis, go ahead.
I have a quick question.
Sure.
So is that power on the on the bottom side? Is it like loss or like what happened exactly to it? Because it got eliminated by the diode.
Yeah, it's in this simple case, it's lost. So it's kind of, you can think of it as lost energy, just wasted.
So no one tried to make something to make it useful or.
Yeah, actually they do. And when you sort of the last thing we'll look at, so again, this is a bit of a spoiler, is once we see how this is done, then we'll see how it's actually done is you actually flip over.
Okay, I was about to say, is there a way to flip the current or like anything?
Yeah, it just gets sort of complex, so we're going to work our way up to that. But it's a very good question.
Thank you.
And you want to make sure you don't waste anything, obviously. Thanks. All right. So anyway, so this is called a rectifier. Somebody last semester asked, where does the word rectifier comes in? I looked it up on Wikipedia or whatever. It doesn't, God knows. I don't know. It doesn't mean anything. It just means to fix something. So just like you would like rectify a situation, the root of the word is the same. I have no idea why people, maybe they're just meaning fixing the voltage. I don't know. It doesn't make any sense to me. But anyway, it's just called rectification. That's basically, as I understand what that means is you block certain polarity of a signal. It could be rectification, could means you block positive and let negative go by, or block negative, let positive go by, or block everything below a 2 volts or 3 volts or some voltage of your choice. But it's basically blocking some below or above some set voltage and letting the other part go. Okay. So anyway, this is a circuit we'll come back to again and again. Okay, this part, and we'll kind of build this black box slowly until we get to this. So that's kind of the main circuit we'll be looking at and as an application example for you guys. Okay, and so basically, what the diode is trying to do in this case is, what we'd like it to do is when it's a positive part of the input, you want the diode to act as a short from the input to the output, so to let that go across. So this is the output, and this is the input. Okay, and then you want the diode to act like an open circuit when you get a negative value. So that way you'll just end up with something like that. Okay, so that's why, and we got some indication that a diode does that. Okay, because again, if we just look at that complicated model of the diode, if we had V sub D, and if we look at, let me just draw the sort of the natural log functionality here. Okay, so the resistance here, the resistance at any point here is sort of tells us if it's a short or an open. Okay, so resistance here it's basically at any point is 1 over the slope of any point on these lines. So basically, if I wanted to figure out the resistance here, I would kind of do something like that, and that approximate there is 1 over R at this particular point. Okay, so the flatter this curve is, the higher the resistance. So here, basically 1 over R implies that you know, R is like a pretty big number. So kind of implies in a flat line, and the slope is flat, implies R is, you know, is very high. Let's say equal to, not quite equal to infinity. It's not completely a flat line, but it's pretty close. And here, you know, a sharp line implies that R is a very low number, let's say kind of close to 0. Okay, so if you look at a switch, okay, when the switch is closed, it has a very low resistance. It has a resistance of 0, an ideal switch, which looks like you can kind of are approximating out here with the diode. And when the switch is open, you have a very high resistance or infinite resistance, and you're approximating that over here. So it seems like a diode can kind of, and also it's like on you know, this side, on say on this side, some way to look at it, this side, this is positive, so this is all positive, this is all positive. It looks like low resistance for most of it, so closed switch. And when things are negative, let's say when things are negative, you have a very high resistance, so let's say an open switch. So it seems like a, you know, a diode would be the ticket. Okay, so let's think about first, like we talked about over and over again this natural log type functionality, and we can't quite forget it, but for a second we're talking about sort of a idealized model of this thing, right? As if it was a switch that was going on and off. We know it's not quite the same exactly, but it's close, and it's really good for a lot of circuit applications, for a lot of analysis. Okay, so this is how you look at it. By the way, I didn't get into this much, and again, this is weird. Don't ask me why these names exist, but the sort of the N side of the diode is called the cathode, and the P side of the diode is called the anode. And I can never get those straight. And, you know, I've been in this business for 25 years. I just remember the diode and how the schematic looks, and the N side and P side. For the life of me, I cannot remember cathode, anode. So it's not going to be the end of it if you can't remember that. But anyway, that's what it is. Okay, so basically when, so you have to remember that another way to look at this thing is if I draw, so this thing is like this. So this is the P side, N side. Again, this is the anode. This is the cathode. Okay, and then if I just draw this as a P-N junction, it would kind of look like this. Okay, and remember that we had, I hope I get this right. This had, you know, the positive ions were sitting here, and the negative ions were sitting here. So the electric field was pointing this way, and so your built-in potential was pointing here. Okay, so basically, if you made this point, if you made the N more positive than the P, you would add to this built-in potential, and you would stop current flow. Okay, so if you made your N more positive than the P, you would be helping the built-in potential resist current flow. Okay, so it wouldn't allow current flow. So this is what happens in this case. When you have the N higher than the P, this is a simplified equation. You can just sort of pretend that there's no current flowing, right? There's a little bit of current flowing, not much. Okay, so you can think of it as an open switch. Okay, so vice versa, if you made the P higher than the N, then you'd be reducing the built-in potential. If you made this positive and this negative, you'd be reducing the built-in potential and you would encourage current flow. So, and that's the situation you have here. When you have the P more positive than the N, it looks like, you know, you could think of it as a closed switch. Okay, so that's the model of a idealized diode, as if there was no natural logs, there's no exponentials, is just these two things. If the anode or the P side is bigger than the cathode, you can think of it as a closed switch. If the anode or the P side is lower than the cathode, you can think of it as an open switch. Okay, so again, this is just a model, idealized model to simplify circuit analysis. It doesn't mean that those natural log functions, et cetera, are out the window. We're just really simplifying the heck out of them, so it makes for easy circuit analysis. Okay, so again, this is just something that I don't know if it helps you guys remember this or not. It doesn't do anything for me, but what the heck, it's a model people use, and it's a way to think about this as if it was kind of a valve, a water valve or something that's hinged on one side. And so if the water tries to go in this way, because there's a stopper on this side and the hinge is this, it basically lets the water go through if it's going from this side out. Okay, but because the stopper is on this side, if the water tries to go that way, you basically, our valve stops the water flow. Okay, so it's kind of a similar idea to that. A water valve that only lets in this, you know, in where you're talking about water current or electrical current, is just an analogy here to, it allows current flow in one direction and not the other. Okay. Okay, so what does this mean? Okay, well, if you start playing around with two diodes, whenever you have, so like if you have two diodes and hooked up like this, so this is two diodes that are like connected front to back, facing each other, okay, this will always be off, because if you can think of it this way, is, you know, you'll let sort of current flow this way. If A was more positive than C, this would be let current flow through, but this guy, D2, would block it. Okay, so it wouldn't get any current there. And vice versa, if C was higher than A, D2 would let current flow, but D1 would block it. So this thing would always be open circuit. Okay, the same thing would happen here. Okay, one or the other one would always block the circuit, so always open circuit. Now here, in the case of A, you could have conduction from A to C, because if A is more positive than C, D1 would let the current flow, and then D2 would also let the current flow. So it would turn on. If A, on the other hand, if C was more positive than A, though, both D2 would block it, and there'd be nothing for D1 to do, but you'd get a block thing. So if you hook up diodes in series, the only way you could get any kind of conduction going through them would be if they're pointed in the same direction. So anyway, when you have diodes in series, you never see them like this. It's kind of like nonsensical. Now you might see them hooked up like this, and there's an output here that goes somewhere that does something. That's okay. But if they're just purely hooked up in series, and hooked up in series means there's like nothing connected to this node, then, you know, these are just doesn't make sense to do these. This is the only way, the only thing that would make sense. Okay, so here's, again, remember our actual, if I was gonna draw our actual diode model, it would look like, if I put voltage versus current through the diode, it would have this exponential thing going through ground, very low current. Okay. Now, if you have, if we use the simplified model, what we do is we have, when things are negative, okay, it's completely an open circuit. So R is infinity and you just have 0. So the infinite case of current versus voltage, again, would be a flat line because the resistance is 1 over the slope of this line. Okay, so when VD is negative, we can just pretend like there's infinite resistance, meaning an open switch. Okay, and when VD is positive, you pretend like it's a dead short. So in that case, the slope of the line is going to be very sharp because the resistance is 1 over that slope. Okay, so the slope is kind of infinite, so resistance ends up being 0. Okay, so you end up with this this is our sort of ideal diode characteristics. Below below ground, and VD is negative, it's an open circuit with infinite resistance. And when VD is positive, okay, you end up having a short circuit. So now one tricky thing is that, I guess not that tricky, but I just wanted to mention it. So when VD is less than 0, R is infinite, okay? When VD is larger or equal to 0, R is 0. Okay, so the tricky part is like, oh, what the heck is going on right at 0? Well, right at 0, the resistance is 0, but also the voltage across that resistance. So this would be, so right here is this funky place is, this would be V sub D. So the resistance is 0 right there, but so is the voltage VD. So you have, voltage that's 0 across a resistance that's 0. You still get 0 current flowing right there at V equal to 0, but you also have 0 resistance. It's just really just doing housekeeping. It's just making sure that we don't have a discontinuity at 0. But basically, you can assume that the diode is on at VD is equal to 0 or greater than 0. Okay, and we assume that the diode is off at VD less than 0. Okay, any questions up to this point? No? Okay. All right. So, I don't know, this is just some funky circuits. I don't know why you would do this thing either, but you could hook up 2 diodes, flipped over in parallel and get it to be a short. Great. I'm not sure what to do with that. Okay, so let's now look at, we had this as we did it as an example. We might have as a homework problem. So if you guys remember what happened, we ended up getting a, what was it? So let me try to do this real time, which is probably a bad idea, but so the real solution here was, V sub A is equal to the diode voltage. So let's call this VD1. And then I'm going to call this VR1. Okay, VD1 plus VR1. Okay, VR1 was IA times R1. And then VD1 was VT natural log of IA over I sub S. And that was, if anybody thinks I got that wrong, please tell me, but I think that's right. And then we basically ended up, that's the equation for this thing of VA respect to IA. And the problem is, so this is with the full natural log model, everything. The problem is there's, as far as there's no closed solution to this. You have VA on one side, you have I sub A in a natural log, and you have I sub A in sort of a linear relationship. So we solve this in our homeworks, etc., in our examples by doing an iterative solution, and it took forever. And we said, oh, this is a problem because this is the simplest of circuits. Okay, so that's the way to solve this circuit if we use the exponential characteristics of the diode. Okay, now let's try to solve it with this, or I don't know what to call it, our brain dead model, where if this thing is positive, more positive than this, it's a short, and if this thing is more negative, it's an open. Okay, so let's try to do that. Okay, let me open up a new page and redraw this thing. So we had V sub A. So we had D1, R1. I get this right? Yeah, I'm hooking up to ground, but really, I guess I could just draw it. Let me just draw it exactly the same. Same difference. Okay, so I'm gonna do this like, we'll work together, gonna do this many times, including your homeworks, etc. Arthur said, I don't think IA times R1 is included. No? Like you're thinking, Arthur, you're thinking this is not included? Okay, so we have to include R to match.
That was like thinking like right there. Like, I remember VT times ln of that, but I don't remember IA times R1. Is that part of something else? Oh, is that for VR1 or?
Well, yeah. So this is VR1 would be this guy.
Oh, okay.
V sub D would
Thank
be
you.
this guy. Sure. It's just basically we're doing KVL. So this has to be this drop plus that drop. Okay. Okay. So that was this thing, and again, painful to solve. So now here's this. I'm feeling like I'm showing you guys a magician trick here. So pay a little bit of attention here. So the way you analyze this is you look at two cases, okay? You look at the case of VA very negative. So it's helpful to think of, I don't think of it as minus infinity or something. Think of it very negative. So if VA is, the reason you do that is because you don't, sometimes the circuits get a little complicated. What you want to do is to figure out, is this higher than this or is this higher than this? So you just think of it as a very negative voltage. So you don't have to worry about, well, what's, if, you'll see later on, you might have multiple resistors and you'll go, what's the ratio of resistors? If you think of it as it's like a very negative, minus 1,000,000 volts or something, there won't be any question. So if VA is very negative, this point ends up being much lower than this point. Okay, very negative. So what does that mean? That means that this guy is going to be a open circuit, okay, when VA is very negative. So the circuit's going to look like this. I suggest you guys always redraw the circuit, okay? I take shortcuts and I always regret it. By the way, this is our V out. So our resistor, Okay, and this is V out. Okay, so it's very negative. Remember that when this thing has, this is more negative than this ends up being like an open circuit. Okay, so what's the equation for this? V out and VA, so just V out. There's basically, this thing's out of the picture because you got an open switch here. So V out is just equal to VA. Oops. Are we doing that? Okay, good. Okay, so that's the case when VA is very negative. Okay, so let's look at a case when VA is very positive. So again, like, plus 1,000,000 volts, so you don't confuse yourself. Okay, in that case, this point is more positive than this point. And then remember that if you have this side's more positive than this side, you end up having a closed switch. So again, I'm being totally brain dead here, and I'm going to redraw this thing with a closed switch. Okay, so V out is VA. Okay, so actually I want to figure out, I guess, I sub A. So I sub A in this case would be 0, right? There's nothing the I sub A could go across, okay? In this case, I have VA, and the switch is closed, okay? So basically now the current has someplace to go. It can go across that resistor. So in this case, I sub A is equal to V over R1, V sub A over R1. Okay, so if I was going to draw this, V sub A, I sub A, okay, when I'm very negative, okay, I sub A is just going to be 0. Okay, so and when V sub A gets positive, I sub A is going to be 1 over R1, the relationship with V sub A. Okay, so that's what we'll end up looking like. And that's sort of how, so notice now, I'm going through the individual steps, and I suggest you two should do that as well, certainly to not screw anything up. But you can almost do this by inspection, get a response of this thing. Whereas, instead of doing a natural log iterative process, I'm just kind of looking at, is the diode on, is the diode off, and what does that mean to the rest of the circuit? And I can get this transfer function, which is approximate, but good for a lot of things. And so we're going to do this over and over again. Now, questions you guys should be asking yourself and will be answering, because we're running out of time here, is how did I know that the crossover would be right there? Why aren't we looking at, because we said very positive or very negative. How do I know, the crossover, it didn't do this or something like that, right? We don't know that, but so I'll show you guys how we do that. And it's also, again, pretty simple math, simple by inspection. But anyway, the gist of this conversation that we're having is that by assuming this really simple model, we can make it a lot easier to analyze diode circuits. Any questions? If no, okay, guys, so thanks, and I'll see you guys on Thursday. Take care.
Thank you, Professor.
Thank you,
See you on
Professor.
Thursday.
Thank you. Bye.
Thank you, Professor.